Yeah, so last time we studied, we derived the action of the Liouville theory, and now I'm going to tell a little bit more about this. So actually missed on the factor of pi the last time, so I cover it now. So we studied on the action of a free boson computed in the metric like mm, maybe we can say that it is e to the w of sigma, and we obtained that up to some up to some normalizations, this w of sigma can be written as as uh, uh, 1 over 6 pi integral of d mu maybe d sigma d bar sigma plus oh, and then normalization of this coefficient does not matter. Mu e to sigma d2 z. Or if we try to compare this this action for the theory with some initial metric is conformal factor sigma 0. If you say that this sigma is a modification of this conformal factor, and then this difference is so it is 1 over 6 pi integral of d sigma d bar sigma plus plus 2, maybe it's up to some definition of r sigma, r0 sigma, plus mu square root of g0 e to the to sigma d to z minus some mu area of this metric. So if we choose a flat metric on a sphere, then this R0 gives a sigma of infinity. And now we can notice the following thing. So we know that we know that a central charge of of uh, of conformal field theory can be obtained, for example, from the dependence of its partition function on a metric. So, namely, let us say that let us call this expression the Liouville action, maybe. So, which one to define? Well, let us say that it is a Liouville of sigma. So we can say that a central charge of CFT can be obtained from this, that the CFT of e to the to sigma g zero is e to c as Liouville of sigma g CFT of g0. And looking at this formula, we can ask what is in the central charge of the Liouville theory itself. So for now, this sigma is not dynamical field. It is just some scaling factor. But we can try to ask what happens when we try to integrate over this sigma. So in principle, we could perform this gauge fixing to reduce the integration to uh, integration over sigma. But now there is a problem. So we don't know. So we want to integrate in sigma in principle. So d sigma. So we don't know what are the in principle we know what is the correct definition of this metric. So in principle we should say that there is so it is some nonlinear measure because if we define uh, some scalar product of uh, small variations of metric delta g, mm, it should be given by the integral of delta g mu nu delta g rho sigma times times oh, maybe it's easier to say that after all, sigma behaves almost like a scalar, so we should have something like delta sigma. Delta sigma is the integral of mm, delta sigma 1, delta sigma 2, delta sigma 1, delta sigma 2, e to the 2 sigma d to z. So that's the only measure which we can write. And the problem is that it is nonlinear. So we then should ask that integral over d delta sigma e to minus delta sigma equals to 1, and this leads to some nonlinear measure. And in principle, people studied what to do with this, but I'm not familiar with these considerations, and I don't know if they were able to get some rigorous result. So So let us just try to say that that this d sigma is just a linear measure, like for the free boson, and see what breaks after this. So we will have some integral. See, so there's integral in d sigma e to let us write some coefficient in this in front of this Liouville action. Mm. That's right. Let us denote this coefficient in Q. Squared over 6 pi integral d sigma d bar sigma plus 2r 0 sigma plus mu and this function, this partition function will be the function of G0. So now we would like to play the same game. Namely, we would like to ask what happens with this partition function when we change G0. So measure in the matrix G0. So mm, now so how to do this? We have this Liouville action. So it is minus q squared I'm not sure that it's a good notation, but mm, no, maybe let us better use some. Let us put here coefficient 6q squared like this. So we have here the following expression minus 6 q squared times times Liouville action, which is itself the difference of W of sigma plus sigma 0 minus W of sigma 0. of the same of this function, which is in the quadratic form. So we can say that if we perform the change delta sigma, we should also perform some transformation with our scalar factor. So conformal, or maybe not conformal, but this Weyl transformation is uh, so we add some delta sigma to sigma zero and subtract it from sigma, so that this first term, which depends on sigma, does not change. So this transformation looks like minus delta sigma. This cancels, and minus w of sigma zero plus delta sigma. So in total, it can be written as original expression, to squared w of sigma plus sigma zero minus w of my that is minus 6q squared as Liouville of sigma whose minus w of sigma zero plus 6q squared w of sigma zero plus delta sigma minus w of sigma zero. And so this equals to our original action minus 6 q squared as Liouville of sigma plus 6q squared as Liouville of delta sigma. Right. So we can now say that if we compute this partition function of g0 times e to delta sigma, then it will equal to the classical contribution. uh, times times quantum contribution, because we decided that this measure is linear. So as Liouville of delta sigma. Times this and this z of g0. So so what we obtained now, that the uh, that central charge of such a theory, by the way, probably here it is, well, I'm not quite sure about the sign, but the consequence is that central charge of such a theory which is equivalent up to the change of variable to the following theory. Theory minus 1 over pi integral of sigma squared plus 2q r sigma sigma over q. The central charge of this theory is 1 plus 6q squared. Okay, so, but here is one problem. The problem is the following, that this that if you say that delta sigma is is 1/2 of so for conformal transformations. So for conformal transformations, delta sigma should equal to this renormalized delta sigma should equal to 1 over, it should equal q over 2 d epsilon plus d bar epsilon, d bar epsilon bar. So e to the so and when sigma goes to sigma minus delta sigma, and then e to the to sigma over q goes to e to sigma over q divided by d epsilon. No, so I should have written here a logarithm actually. So I don't want. No. like this is fine. No, not fine. dw over dz, dw bar over dz bar. So it transforms. It is divided by the w over dz, the w bar over dz bar, which means that a dimension of this exponential, classical dimension of this exponential, is equal to 1, to 1, 1. And but quantum corrections break this property. So we have that delta quantum of 2 sigma over q. So it depends on normalization, but in such normalization, which I doesn't here, this dimension equals to 1 over 1 over q squared, like this. And if you combine these two dimensions, then we get something like 1 over q squared, 1 over q squared. So a combination of this is wrong. And oh, so actually no, it is with minus sign here. And to fix this, let us say that e to the 2 sigma over q is replaced by e to the 2b sigma. And compute the dimension of the separator. So it will equal e of the dimension of this 2b sigma. Classical dimension of this will equal to b over q, b over q. No, what I'm writing. bq, bq. And quantum dimension b to the 2b sigma will equal to minus b squared minus b squared. So delta of b equals to 1, delta of e to b sigma equals to 1, 1 is equivalent to the equation bq minus b squared equals to 1, or it means this parameterization that q equals b plus b inverse. And this way we came to this Liouville parameterization of the central charge, So this Q equals B plus B inverse, C equals 1 plus 6Q squared, and delta equals to delta of alpha equals to alpha Q minus alpha. So is it clear?
But the classical dimensions, you deduce them from the fact that it should, or how it transforms like classically under a
Yes, because we see that here to make this theory conformal, we should add some non-trivial transformation property for sigma. So when we change metric, we should also shift sigma by the logarithm of Jacobian.
and the classical one is deduced from the like the normal ordering.
No. The classical. Oh,
the quantum one. Sorry.
yes. For the quantum dimension, we say that this interaction term can be neglected, and we can compute this ultraviolet divergence related to the normal ordering. So it's computation like for the free theory, and we assume that that a integration measure is as for the usual boson. So is it fine?
Yeah.
Mm-hmm. Okay, so we have this parameterization. So and in some sense, this Liouville theory is a kind of generic field theory, especially if it is for something greater than 25. So we can also think about this parameterization, like if we are interested only in real C's, let us say that central charges are real. Then when so when B is let us write somehow. So what happens when B is real? Then B plus B inverse is greater or equal than 2, and so C is greater or equal than 25. And of course, B equals 1 is C equals 25. And there is also a reason when B is purely imaginary. And then people introduce some quantity like B equals to I beta, and then central charge equals to 1 minus 6 q squared, 6 beta plus beta inverse squared. And for example, so it is C is less or equal than 1. And if we say that beta is a square root of P over Q, then C equals to what 1 minus 6 mm, 1 minus 6 p minus q squared over pq. Like for example, when beta equals to 1, c equals 1. When beta equals to 3/4, then c equals to 1/2. Something like this. And there is also one region when b equals to some I phi. In this case, c equals to 1 plus 6 plus 24 cosine squared of phi. So it means that c is from 1 to 25. And the difference between on this domain and other two domains is that in this case b and so in this case b and b inverse generate the two lattice. Like there is b and b inverse, there are some complex numbers. So and usually there are usually people want to write some difference relations which involve shifts by b and b inverse, and if their ratio is not a rational number, then you can say that if some function is doubly periodic in b and b inverse, then and there is and this function is a constant. But if but then there can happen two phenomena. First is when b and b inverse are real or purely imaginary, and their ratio is rational. In this case, there are non-constants which are periodic under b and b inverse. But if we and if we are between 1 and 25, then it happens in all situations. We have infinitely many W periodic functions, and so it means that this complex Liouville theory is well, it is very well defined for C greater than 25. We can define something similar to Liouville for C less than 1. And what happens between 1 and 25, it's a more complicated question.
Can you write it, Pasha?
Hmm?
Can you write it down?
Well, but I don't know what to write. Well, maybe maybe we can write. Well, when when c is greater than 25, uh, mm, and when well, when b squared is not rational. When c is less than 1, and then the same. But when c is from 1 to 25, so as a consequence, when c is uh, so when c is mm, when c greater than 25, or c is less or equal than 1, mm, shift equations like f of a plus b equals to like usually the linear shift relations, like f of a plus b plus c1 c2 f of a plus c3 f of a plus b equals to f of minus b, and maybe some coefficient. Oh, mm. So if we have some difference equations satisfied by some functions, and such systems define define function f uniquely. And this f can be a structure constant. This can be a fusion kernel. So in and if you are in this region greater than 25 or less than 1, then if you manage to find some solution of pair of such difference equations, it means that we found it means that the solution is unique up to constant, and because of this a lot of objects are well defined in these regions. But for intermediate central charge from 1 to 25, in principle, they can involve some periodic functions. And also, there is some funny observation that if you combine central charges for B and IB, then their sum will be 26, and as I told, if you want to integrate all metrics, we should add a BC system with central charge 26. So it means that some conformal theory with parameter IB, and then a Liouville gravity with parameter B, and BC system form precisely a system of central charge 0. And we can compute something in this theory. So it is a bit nice that this 26 is visible even here. So are there any questions about this?
No.
Okay, but now I want to tell about a classical limit conformal blocks. And first of a classical limit of the Liouville theory. So I want to compute this partition function, or maybe better to say that we start from computation of some correlators. So we want some alpha 1 of phi of z sigma of z1 e to alpha n sigma of zn e to minus 1 over pi integral of d sigma d bar sigma plus mu e to the, oh, in principle, we should write also this term with coupling to curvature, but let us neglect this. Let us just remember that there is that there is some delta function at infinity. D sigma d2c. Let us drop this down. So I want to do this integral d sigma. So if you want to have classical limit, then it is natural to send b to 0 because what? Because you can say that let us rescale this sigma and by b. And then we will have alpha 1 over b, sigma of the 1, e to alpha n over b, sigma of the n, e to minus 1 over pi n b squared, and of the sigma, the bar sigma plus mu b squared e to the 2 sigma. And so we see that the action of the Liouville is now rescaled by, so we can call this variable like mu tilde, like let us denote it, let us say that it is our new mu. Because this is not important. This mu can be made 1, it can be made any number by just shifting sigma by some constant. So let us say that it is mu, but the observation here is that this action scales like 1 over b squared, and now we should decide something about these exponentials, which are in the prefactor. So there are two options. So when they scale like 1 over b, it's something not very interesting because they cannot they are not of the same order as the action, but they are big. They are still big. So this is something not very nice, and we actually want to consider the fields such that the alphas behave like 1 over b, alpha I tilde. If we choose such scaling of their charges, then these exponentials will be of the same order as this classical action, and they will affect the classical equations of motion, if you want to consider a saddle point. And another opposite case is to say that this alphas equal to b and beta i's. Maybe let us start from some tildes and then make this choice. So let us compute the dimension of such field. Delta of 1 over b alpha I is So let us write on the scaling of Q and C. So Q is of order 1 over B, so it goes to infinity, and C is of order 6 over B squared, so it also goes to infinity. B goes to 0. So now delta of on this 1 over B alpha I equals to 1 over B squared, proportional to 1 over B squared, alpha I times 1 minus alpha I. And in this case, delta of B and beta I is mm, just beta I. So one dimension goes to infinity, like 1 over B squared. Another dimension stays constant. So so now we can write that this this correlator equals to the path integral the sigma e to some number of light fields times exponential of 1 over B squared minus 1 over pi Liouville action of sigma plus sum of alpha I is maybe put some points W I is alpha I is of sigma of the i's. And if you now try to compute this by saddle point, then it will equal to E to let us denote this object of f of sigma. It will equal to f of sigma classical 1 over B squared. So it's some number which on the sigma classical depends on alpha 1 and depends on all these alphas. Times the product of these exponentials e to beta I sigma of sigma classical of all these alphas computed at point Wi. So there is such a decoupling. So I have heavy fields affect saddle point equation and give this prefactor which equals the action on the saddle point. And light fields are just probes which take the value of this classical solution and they take this value of classical solution at some point and it is the answer. So, for example, we see that in the leading order, the correlator does not have singularities when WIs collide in between itself. So, are there any questions?
Can I ask? In some cases, doing the rescaling by decoupling constant, like you did in the beginning, like rescaling by B, in some cases gives an anomaly. And is there any motivation why does it happen here?
But what do I mean? You mean this scaling of sigma by a constant?
Yeah, by B.
But we computed so here it is even simpler than in the actual theory of arithmetic. Here measure in sigma is just linear measure, so so there is no place for anomaly. It is just a shift of the zero mode.
Okay.
Well, there is also there is of course classical prefactor. No. Sorry, it's not a shift of zero mode. It is a rescaling of all other modes. Mm. But if we say that when we think about anomaly, we can forget about this Liouville potential, and in this case, we know that this path integral is just a determinant of Laplacian. So yes, 2 power minus 1/2. So how can it change if we perform some rescaling? So it's not like some nonlinear theory when we change our overall coupling constant in front of the determinant. It is some trivial transformation in this case. Did I answer on
Yeah.
okay.
And there is no, okay, this is the classical piece from the saddle point, but there is no correction like one loop.
Of course, there are corrections times probably some 1 plus all of b squared, and so here we have plus all of 1. So they are all there, but so this all of 1 is a function of I think well, probably it's function of everything. No, maybe of alphas only. Yes, there will be some correction to this classical action, and also mm, some determinant corresponding to some determinant of Hessian of this action plus of this action computed on the classical.
Mhm.
Let us maybe write this term also. This is of sigma classical times something like 1 plus all of b squared. And because of this, if you consider the ratio of correlators of e to product e to alpha I f sigma of the i's 1 over b times some other operators on that are light operators. Divided by product of e to 1 over b of phi sigma of the I. It equals to uh, this operators of sigma classical at point W1, maybe like this, Wn of sigma classical or Wn. Right. So now we can also think about it this way. So when we compute this partition function, so this is some integral over. So so we know that any correlator and CFT can be expressed in terms of conformal blocks. So we can draw some picture like there is a conformal block alpha 0, alpha 1, alpha 2, like some alphas over B. And there's some operators, O, On here. And here we have some intermediate dimensions which we can say that intermediate charges. Which we can say that they are also big because uh, because like like object in general position will be big. Like 1 over b is the natural scale for these charges. So we have some gamma 1 over b, gamma 2 over b, and here we have points like z0, z1, z2. It is a conformal block. Then we have a conformal block of the same kind with anti-holomorphic variables. So we think that all these objects are real. So to z0, z1 bar of 1 over b. And there is z2 bar of 2 over b. Here we have gamma 1 over b again. So that holomorphic and anti-holomorphic dimensions are the same. Some O1, some other fields, O1. So that these are conformal blocks. And this is also multiplied. So and this is also multiplied by 3-point functions like c of alpha 0 over b, gamma alpha 1 over b, gamma 1 over b, c of gamma 1 over b, alpha 2 over b, gamma 2 over b, and so on. So I don't want to write this explicitly, and just saying that there is such some object of this kind. And we should integrate over intermediate charges. So there is some integral d gamma. And we know from our analysis of the classical of this QFT expression that the answer of this is e to 1 over b squared. Oh, 1 over b squared. Some f of sigma classical times a product of operators O computed at the this classical action. And there's a question like when can it happen that the integral of some object which depends on b behaves like e to 1 over b squared times something, and conjecture that this object can be obtained as maybe this notation f small is not very big, is not very good. Let us use some notation s small, or maybe just s. We change it. Right, it's only in 2 places. So, the natural conjecture is that all these objects behave in the same way, like a conformal block of this kind of a 0 over b, 1 over b, 2 over b, gamma 1 over b, and so on, some O1. So it equals to some function 1 over b squared f of 1 alpha something z1 z something. At times, product of functions, some functions all of wi, maybe let us better write how many alphas we have, alpha m. Also on gammas, z1, and so on zm. And a product of some function which depends only on one variable, wi, and also on this alphas, gammas, and z's. So it is a conjecture for conformal block, and also the same conjecture for the 3-point functions. C of alpha over b, beta over b, gamma over b times equals to 1 over b squared, some c of alpha, beta, gamma. 1 plus all of b squared. Maybe no. Plus all of 1. Here plus all of 1. So if this conjecture is true, then e to 1 over b squared s of sigma classical is extremal value of computed in this intermediate dimensions gammas of this e to 1 over b squared 1 over b squared f of alpha, gamma, z plus f of alpha, gamma, z bar. Times the separators. And I did know in which cases this conjecture is proved, starting from some explicit formulas for conformal blocks, but in principle, it is clear that it is true. There can be no surprises, and if you take some arbitrary conformal block and compute and compute this object, like take the logarithm of conformal block. So you can, for example, expand it. So it's some function of z. It is some series. Well, maybe how to explain it better. So in principle, conformal block is some function. If you put here alpha 0 over b, alpha t over b, alpha 1 over b, alpha infinity over b, and gamma over b. So if we write this conjecture, then it tells us that it is 1 over b squared. So the leading term is 0. C1 z plus c2 z squared. It is t. C1 t C3 t cubed. So if we try to open these brackets, we see that it equals to, and let us write something plus O of 1 plus A1 t plus A2 t squared plus A3 t cubed plus and so on. So if we try to expand it as a series in t, then it tells us what it is 1 plus t c1 over b squared plus a1 plus t squared. And here we have what we have c1 squared over b fourth plus c1 a1 over b squared plus and plus something else plus a2 plus just a2. I also missed plus c2 over b squared plus a2. Then t cubed c1 cubed over b6 plus c1 squared a1 over b fourth plus well, I don't want to write the remaining terms, but I see the principle that uh, if we look at the expansion of conformal block itself, then its coefficients have this arbitrary big singularities in B. So it is not true that the conformal block itself has an expansion when B goes to 0. And trivial statement is that if we take logarithm of this series, then each coefficient has a singularity not bigger than b minus 2. And so we can check that it is true order by order, for example. And the definition of classical conformal block is that so if you say that normal conformal block is f of alpha 0, alpha 1, alpha t, alpha 1, alpha infinity, gamma, B and T is a conformal block. Then a limit when b goes to 0 of this object, b squared logarithm of f of alpha 0 over t alpha t over b, alpha t over b, alpha 1 over b, alpha infinity over b, b t. So this called some function f of alpha 0, alpha t, alpha 1, alpha not enough space. Gamma and t. It is a classical conformal block. And if we want to and they can be computed. There are some explicit functions. And so looking here, we can understand that if we want to compute partition function of the Liouville theory, which is a function of z and z bar and not of intermediate dimension. So if we want to compute this, we need to solve an equation for gamma, which is precisely this saddle point condition. So there will be some equations which have to be solved, and it will give some classical dimension. It is a bit similar to a saddle point computation on the path integral, but here it is just some finite dimensional integral. So classical, or it is also, it's also called C equals infinity. And by the way, there is the following remark. So yeah, you might remember that there was also the Gavrylenko limit. So in that case, C was fixed, and deltas were sent to infinity, like 1 over epsilon squared delta, maybe delta tilde. So those two limits can and so in principle, you can still perform the Gavrylenko limit here, because if you send dimensions to infinity faster than the central charge, it will correspond to the Gavrylenko limit taken from the classical conformal blocks. So in this case, remember that conformal blocks behaved like 1 over epsilon squared. 1 over epsilon squared Gavrylenko per potential. So this can be understood. So now we can introduce a parameterization in which we can take both of these limits. And with this kind of AGT parameterization, so it is B equals to epsilon 1 over epsilon 2. And so Q equals to 1 plus 6 epsilon 1 plus epsilon 2 over epsilon 1 epsilon 2. And deltas are parameterized by something like this. So so by the way, this classical conformal block it is also called Nekrasov-Saakashvili limit. Maybe let me write it here. So in this parameterization, we can say that alpha is always fixed, and we can send epsilon 1 is a fixed, epsilon 2 goes to 0. So we see that then oh, it is central charge. In this case, central charge will be mm, 1 plus 6 epsilon 1 over epsilon 2, so it goes to infinity. And delta will be alpha epsilon 1 minus alpha. Oh, sorry, it is squared. 6 epsilon 1 squared. Epsilon 1 epsilon 2. Oh, no, it's not correct. Sorry, it is epsilon 1 plus epsilon 2. Oh. Oh, probably I also wrote something here. No, here it is fine. So here it should be epsilon 1 epsilon 2 plus 6 and this. So it is 6 epsilon 1 over epsilon 2. This one should be correct. And this delta also goes to infinity. So, moment. So it is called so in this case conformal block behaves like e to 1 over epsilon 1 over epsilon 2 conformal block of epsilon 1 and everything else, alpha, z, and so on. And this epsilon 2 appears as the overall factor. But we can also perform another limit when epsilon 1 goes to 0 and epsilon 2 also goes to 0. We can say that they go to 0, for example, in the same speed. So in this case, this conformal block. So you see, this scaling means that so if epsilon 1 and epsilon 2 go to 0 with the same speed, then central charge is fixed. And this delta behaves like 1 over epsilon 1 times epsilon 2. So delta is something like minus alpha squared over epsilon 1, epsilon 2. So in this case, we recover this Zyber-Witten limit. E to 1 over epsilon 1 epsilon 2 Zyber-Witten potential. So it is an S limit in Krasov-Shatashvili. And this is Zyber-Witten limit. So is it fine?
Yeah.
Okay. Now let me tell one funny thing, which is more or less obvious, but nevertheless nice. So let us try to solve classical Liouville equation. Try to imagine that we find a solution that we are finding a solution of this saddle point equation. So up to some factors, scalings and so on, we can write that this equation is dd bar sigma is mu e to the 2 sigma. So it's some nonlinear equation, and in principle it might be unclear how to solve this. But let us consider the following object. Let us consider the object e to the minus sigma, and try to compute its no, not this one. Let us try to consider the following object t of z, which is d2 which is d sigma squared plus d squared sigma, and maybe minus d squared sigma. Let's define such an object and compute its d-bar derivative. So it is 2 d bar sigma d sigma minus d of d bar sigma. So now substitute what is d bar sigma. It is 2 mu e to the sigma d sigma, and another term is d mu e to the sigma. So this is it is 0. So this so this object therefore is holomorphic. And also we can consider t bar with bar derivatives, and it will be anti-holomorphic. But now we might ask, who is this t? How to relate it to sigma? So if you know a t, so if you want to solve this equation, we can first find some t, a holomorphic function, and then try to reconstruct sigma from it. And to find who is t, let us notice the following. So let us consider t squared of e to minus sigma. It equals to d sigma squared e to minus sigma minus d squared sigma times times e to minus sigma. So therefore, not sure about signs, but probably, well, probably they should be correct. So we find that d squared minus t of z e to the minus sigma equals to 0. And in the same way, d bar squared minus t bar of z bar e to minus sigma is also 0. So if we want to construct a solution of the Liouville equation, we should first choose some t of z. Find two solutions of this equation. And then construct construct such a formula for the metric. Some matrix Cij psi I of z psi j of z bar. Maybe better to write like this. By the way, is it clear that this Liouville equation is a classical Liouville equation is is an equation for the metric of constant curvature, because it is a scalar curvature multiplied by square root of metric, and this is a square root of the determinant of a metric, and this is just square root of the determinant of a metric. Mm. So and so this should be single valued in general case. So as some simple example, we can consider uh, we can consider T of z equals to 0. Then psi 1 2 equal to 1 and z, and e to the sigma can be either so we can construct different combinations. Mm, 1 over imaginary part of z. Well, actually any conformal transformation of this domain. So maybe, well, better to write it as 1 over 1 plus minus absolute value of z squared. So it's Fubini studio metric. And by the way, who knows what is the meaning of this equation? Like how to understand that we have something of this kind?
In what sense?
Well, how to conjecture that we should have a equation of this kind if we don't just obtain it, but if we think about this in the CFT terms? Did we see anything similar to this before?
The BPZ equation?
Yes, precisely. So this exponential e to minus sigma is uh, 5 on 2 field. So also speaking about heavy and light fields, so delta 1 2 in this case, mm, 2 1. mm, so so we have alpha equals to 2b for the Liouville exponential. Oh no, alpha equals to b for the Liouville exponential. And alpha, oh no, yes, to B, and alpha equals to minus B over 2 for the phi to 1. So it is a field that has that has a finite dimension in the limit b to 0, and we see that a relation that one is e to sigma, another is e to minus sigma. So this is precisely BPZ equation conjugate to it. And also we can consider this equation with some singularities like so if for example T of z is alpha over z, then maybe delta over some constant over z, maybe better write over z squared. Write some L minus 1. Then d2 psi equals to, so if we say that now psi is z to power a, then we get that d2 psi minus t of z psi equals to a minus 1 minus l minus 1 over the squared psi. So a equals to l, or maybe 1 minus l. And so we should so if L is some arbitrary number, we should construct a metric which is simple valued. So we get e to sigma equals to something like absolute value of z power l plus some constant absolute value of z to power 2l to minus 12 minus 2. And we see that there is some singularity in this metric. So when z goes to 0, one of these terms dominates. For example, let us say that L is greater than 1. When z goes to 0, e to the 2 sigma, so e to the 2 sigma dz bar behaves like maybe let's put constant here. It behaves like z to 2 minus 2. No, squared absolute value of 4L minus. So it is z to some power like 12 minus 1. So it's value squared. So it means that we have a conical singularity. Because this metric can be written as a flat metric, but to do this, we should perform the change of coordinates, which which takes some power of the complex variable. So it means that and the singularity is precisely the singularity which corresponds to some primary field under the correlator. Since T of z is the expectation value of the energy momentum tensor, then this corresponds to some exponential, approximately of power L. So if we want to compute correlators with the exponentials, it means that we need to look for a matrix with conical singularities at some points. And so in this case, we are able to solve this equation. If we have three singular points, we will still be able to do this because it will be hypergeometric equation. But if we go to, for example, to 4 points, then this equation becomes Cohen equation, and um, uh, actually at that moment this correspondence inverts in a sense that we can tell more about the Cohen equation knowing about CFT than to tell something about CFT knowing about Cohen equation. So maybe that's all for today. Do you have any questions?
No.
Okay, so then thanks for your attention.